Hello everybody. I'm going to talk about a data-driven choice of misfunction for FWI using reinforcement learning. My name is Bingbing Sun and the co-author is Tariq Al-Khalifa. As we know, cycle skipping is a critical issue in waveform inversions. Here we show a machine model which is inverted with L2 norm and with advanced cycle skipping free misfunctions. We can see that cycle skipping is a critical issue as long as the initial model is not accurate enough or we do not have actual low frequencies. It will create problems and create artifact geological models that is not reasonable for interpretations. So the conventional solution is that we want to get a highly accurate initial model or we would want to acquire very low frequencies, for example, below 1 Hz. But these conventional solutions has limitations in some aspect. For example, the initial model is rather difficult to build based on the current industry standard is mostly based on ray tomography. Some complex regions like salt body is very difficult to have a very accurate initial model. Also, to obtain very low frequencies is very costly. Also, there are some old seismic data. Their low frequencies considered to be relatively high. So, our solution can be considered a cost-effective solution is that we want to design more robust misfunctions. For example, now people developed more advanced misfunctions using like matching filter or optimal transport. Those advanced misfunctions can mitigate the cycle skipping successfully. However, they usually sacrifice the resolution. For example, here we're using a shift signals and draw the different misfunction regarding to those time shift. We can see that the advanced misfunctions such as matching filter and optimal transport all shows better complexity than L2 norm. But we can also notice that the complexity would reduce resolution. In FWI, we design to achieve a model with high resolution without cycle skipping. Thus, we normally do is at initial iterations of inversions, we use the cycle skipping free misfunctions. And then later, we perform the inversion using a high resolution misfunction such as L2 norm. We can manually do this, but it's better to perform such switch automatically at the desired critical point. This decision making is widely studied in optimal control. Specifically, reinforcement learning has been adopted to solve this kind of problem efficiently and successfully. Such decision-making problems are general in optimal control. The agent would interact with the environment and get information about the current state, and then the agent tries to make the optimal decisions to get higher rewards from the environment. For example, in video games, the state can be the raw image from the screen, while the action is turned left or right. The reward can be higher marks or win. In machine learning, reinforcement learning algorithms are widely used for such decision-making problems and have shown great success already. There are many reinforcement learning algorithms. In our study, we select the deep Q network. In short, it is called DQN. It is kind of model-free reinforcement learning algorithms, and it is popular, and it is especially suitable for dealing with discrete action space. Like in our case, we only select from 2 candidate misfunctions. Back to our problem. If we try to learn an algorithm which can auto-select the misfunction for FWI, the state S would be the predict and measure the data, and the action A would be which misfunction we should take. The intuitive thinking is that when the predict data and measure data are close, we should use LT norm for high resolution, while in other cases, we should use a more convex misfunction to avoid cycle skipping, such as the optimal transform matching filter recently we suggested. We use the deep Q networks method, the DQN, for our problem. In deep Q, we learn a Q function. Such Q function is represented by a network. For different states, Q would predict the reward we can get for taking certain actions. For example, when the predict data is close to the measured data, we expect Q gives high value for L2 norm misfunction and vice versa. In training, we have trials and try to learn how to make the correct decisions. In reinforced learning, there is an important concept called exploration and exploitation. Exploitation chooses a greedy action to get the most reward by exploiting the agent's current action value estimates. But being greedy with respect to action value estimates, it may not actually get the most reward and lead to suboptimal behavior. Exploration, on the other hand, allows the agent to improve its current knowledge about each action, hopefully leading to long-term benefit. Improving the accuracy of estimated action values enables the agent to make more informed decisions in the future. When an agent explores, it gets more accurate estimates of action values, and when it explores, it might get more reward. However, we cannot choose to do both simultaneously. So one strategy used is called epsilon greedy action selection. So epsilon greedy is a simple method to balance exploration and exploitation by choosing between exploration and exploitation randomly. So we have epsilon, which refers to the probability of choosing to explore. Here we show how the DQN work. Actually, in DQN, we take a single move action and see what reward R we can get. Then the R plus Q S prime A prime becomes a target we want Q S A to be. For example, since all Q values as black circles are equals to 1 now, if we move the joystick to the right and score 2 points, we actually want to move QSA closer to 3 now, that is 2 plus 1. As we keep playing and iteration, we will maintain a running average for the Q value. Such values will get better and better, and with some tricks, the Q value will converge. Here we describe about the deep Q learning algorithm. DQN is the offline training algorithm. Thus, we initialize the replay memory buffer D to a capacity N first, and then the action value function Q is randomized with weight theta. We initialize another target action value network Q with the same weights. We will loop over M episodes, and for each episode, we iterate over T steps. We will take the action based on the epsilon greedy strategies, that is, select a random action or select the action based on current Q value. We will execute the action and above the reward and get next state. We store the transitions ST, AT, IT, ST plus 1 in the replay buffer D. And then we sample randomly of the transitions from the replay buffer D. We will compute the expected reward YT based on the target Q function. and the misfunction can be formulated by the difference of expected reward yt with that output from the Q network, and its gradient will be used to update neural network parameter. Then, after every 6 steps, we will set the touched Q network to be the Q network. We consider a mini FWI example here. The forward modeling corresponds to a model travel time shift signals. Here, the F is the mean frequency, and the tau is the travel time parameter. It's the same as the model parameter in conventional FWI. And our target is to get the highest reward, and the reward is defined as the negative of the L2 norm of the data. We want to train the Q network to take actions and achieve the large accumulated rewards throughout the FWI steps. And we define the Q network as 2 lengths of the input traces, because that input is the predict and measure data. And we only have one hidden layer of size NT, and the output of size 2 indicates the Q value for choose defined misfunctions. In the training, we run 10,000 FWI, and in each FWI, we have 12 iterations. We can see the reward rates when the training proceeds. Here, we show the loss for one episode FWI, and the travel time difference is chosen beyond one cycle. We can see that L2 norm failed to update, while the advanced misfunctions OTMF shows convergence, but compared to the neural network later one, the DQN, it shows faster convergence. As the DQN has learned to use the advanced misfunctions such as OTM at the initial iterations to avoid the cycle skipping, but when the date come too close, the DQN will try to use L2 norm instead. Here we show the Q value for different state. As we said, the state is represented by predict and measure data. And here we plot the different time shift difference between the predict and measure data. And we can see that when the travel time difference is small, the L2 norm has larger Q values, meaning that we should use L2 norm function when the travel time difference is small. However, when the travel time difference becomes larger, the Q value for the OTMF is become larger. That means the Q network tells us we should shift to a more advanced misfunction to avoid cycle skipping. And below figures shows the actions we should take, which is simply the comparison of different Q values, and we select the largest one to be our actions. So we come to our conclusions that we use DQN and shows the toy example to demonstrate that reinforcement learning can help with decision making in FWI. Of course, here is we only use a rather simple example, but we demonstrate the ability of machine learning to learn from running tens of thousands of FWI. And thank you for your attention.